A steel trowel scrapes across a band of pale, crumbling mudstone. The blade stops at a thin, dark ribbon cutting horizontally through the rock wall. This line is a global marker. It forms the physical boundary of the late Cretaceous, about 68 million years ago. Below this narrow strip of compressed ash and iridium, the sedimentary layers of the Hell Creek Formation are packed with the fossilized remnants of a vast, subtropical coastal plain. Above it, the bones of large dinosaurs vanish entirely. This boundary gives us a hard stop. It draws a definitive line in geologic time. But knowing exactly when an ecosystem collapsed does not tell us how it functioned while it was alive. The popular imagination has long filled these ancient floodplains with a perpetual theater of combat. We picture the apex predator, Tyrannosaurus rex, locked in a thundering, earth-shaking struggle against a massive, armored fortress. We want the rocks to surrender a frozen snapshot of an arena battle. But paleontology rarely works in perfectly staged dramas. The ground gives us fragments. And those fragments tell a much quieter, far more complex story about the biological economics of survival. If you walk the aisles of a major museum collection housing material from the Hell Creek Formation, you will pull open drawer after heavy steel drawer filled with the bones of herbivores. The overwhelming majority of these fossils belong to the duck-billed Edmontosaurus or the horned Triceratops. Field records and specimen catalogues from these layers indicate that these animals were the massive, rolling herds of their time. They left behind thousands of teeth, ribs, and femurs. But when you look for the remains of Ankylosaurus magniventris, the inventory drops drastically. It is a remarkably scarce animal in these deposits. This statistical scarcity immediately changes our interpretation of the landscape. An animal that is rare in life leaves an even fainter signal in death. We cannot simply assume that a predator encountered this specific armored giant every time it stepped out to hunt. The sheer abundance of other prey suggests a food web where calories were far easier to acquire elsewhere. But rarity is only the first constraint we must navigate. The second constraint is the physical condition of the bones themselves. Out in the Badlands, a field crew marks a quarry grid. Yellow flags flutter over a scattering of isolated, heavily weathered blocks. There is no articulated skeleton here. There is no intact, beautifully preserved specimen of Ankylosaurus magniventris lying exactly as it fell. Instead, there are dense, isolated lumps of bone that feel entirely wrong in the hand. They are exceptionally heavy. They lack the typical long, graceful curves of a limb or a rib. These are osteoderms, literally, bone grown within the skin. Preparing one of these osteoderms for extraction is a physical ordeal. Liquid consolidant is dripped into the hairline fractures, binding the crumbling edges so they do not disintegrate upon moving. Strips of burlap are soaked in plaster and wrapped tightly around the exposed rock, forming a rigid, protective jacket. The sheer mass of even a single large armor plate requires multiple people to roll it onto a transport sled. When the animal died, the soft tissues, the connective fibers, and the thick skin that held this intricate suit of armor together quickly decayed. Without that biological netting, river currents and scavengers easily scattered the heavy plates across the muddy floodplain long before they could be buried and fossilized. Back in the preparation lab, the plaster jacket is cut away. An air scribe, functioning like a miniature pneumatic jackhammer, slowly chips the surrounding sandstone matrix from the surface of the osteoderm. As the bone emerges, we scan the surface with handheld lasers. This translates the physical object into millions of digital data points. We import this geometry into a computer, building a digital wireframe of the animal on the screen. When we map the isolated bones we actually have against the vast negative space of what is missing, the reality of our limits becomes entirely visible. Because complete skeletons of this specific animal do not exist, we are forced to rely on the anatomy of its slightly older, more completely preserved relatives to fill in the gaps. What stands before us on the screen is a reconstruction, Tightly constrained by the few anchor points, the Badlands have surrendered. SRC-01, Arbour and Curry. 2015. This wireframe model is where our investigation begins. To truly understand how an ecosystem balances the ultimate bite against the ultimate armor, we have to look past the surface of the myth. We cannot simply look at the intimidating shape of an osteoderm and declare it an impenetrable biological tank. To understand how much force this armor could actually withstand, we have to cut it open. A high-pitched whine fills the preparation lab as a diamond-tipped saw blade bites into the edge of an osteoderm. A steady stream of water acts as a coolant, washing away a gray slurry of pulverized rock and fossilized bone. The process is painfully slow. To the touch, the fossil feels as dense and unyielding as a granite boulder. If you were to simply weigh this block on a scale, you might assume that during the late Cretaceous, about 68 million years ago, this animal survived by encasing itself in a solid, impenetrable shell. But pure it is a biological liability. Solid, rigidly dense bone is brittle. Under extreme, concentrated pressure, a solid plate will simply shatter, driving bone shards inward. Evolution does not favor biological designs that break catastrophically upon first contact. To understand how this armor actually functioned, visual inspection of the surface is not enough. We have to look at its cellular architecture. Once the saw finally passes completely through the osteoderm, the severed block is taken to a lapidary wheel. The freshly cut face is polished until it is perfectly flat. It is then glued with industrial epoxy to a small glass slide. The remaining bulk of the rock is cut away, leaving only a thin wafer of fossil attached to the glass. This slide is then ground down using progressively finer silicon carbide grit. The technician stops frequently, wiping the slide clean and checking the thickness. They must grind the bone down until it is barely 30 microns thick, so thin that it becomes translucent. Only then can it be placed under the lens of a polarized light microscope, when the light clicks on and shines up through the glass. The myth of the solid rock tank dissolves immediately, through the eyepiece. The internal geography of the osteoderm is revealed in vivid, microscopic detail. The bone is not a uniform, solid mass. Instead, cross-sections reveal a distinct structural hierarchy. There is a dense outer cortex, a hard shell that forms the visible surface of the armor. But beneath this thin outer rim, the vast interior of the osteoderm is highly porous. It is made of cancellous, or spongy, bone. SRC-03, Carpenter. 2004. This internal space is an intricate, three-dimensional lattice of intersecting bony struts. Under polarized light, the alignment of the fossilized collagen fibers within this lattice becomes visible. The fibers are woven in alternating directions, creating a structural fabric that is remarkably complex. This is direct evidence of a biological crumple zone. The woven bone fibers are arranged to dissipate impact energy, spreading the kinetic shock of a localized strike outward across the entire plate. This changes our interpretation of the animal's defensive strategy. This armor was not designed merely to deflect an attack. It was biologically engineered to crush inward, absorbing massive amounts of kinetic energy without failing completely. It is a shock absorber. By utilizing a spongy interior, the animal also drastically reduced the overall weight of its armor compared to solid bone. But even with this weight-saving adaptation, carrying thousands of these plates embedded in the skin required a massive physiological investment. The sheer mass of the dermal armor anchored the animal to the ground, forcing a low-energy, slow-moving lifestyle. The biomechanical trade-off is absolute. The animal sacrificed speed and agility for resilience. On the digital wireframe model, we can map where these large osteoderms sat across the animal's back and flanks. But the computer model also highlights a severe limitation in what the fossil record preserves. When we look closely at the outer surface of a well-preserved osteoderm, it is not perfectly smooth. It is heavily textured, pitted, and scored with tiny grooves. In life, these grooves were the channels for blood vessels. They fed a thick sheath of keratin, the same tough protein that forms human fingernails and the horns of modern rhinoceroses. This keratin layer would have capped every single bony plate. It added a hardened, resilient outer shield that provided even more shock absorption before a predator's tooth ever reached the bone itself. But keratin is a soft tissue. It decays rapidly after death and almost never fossilizes in these sandstone environments. We are left with a hard constraint. We simply cannot know the exact thickness of this missing keratin sheath. It may have added a few millimeters of protection. Or it may have added several inches of rigid, horn-like material to the tallest spikes. Without it, our computer models can only calculate the baseline strength of the bone. We know the armor was a highly effective biological shock absorber. But to understand if it was effective enough to guarantee survival, we have to test it against the pressures of its environment. We must calculate the maximum force that the ecosystem's apex predator could deliver. A massive, heavy skull rests on a foam pad in the center of the lab table. It is the upper jaw, the maxilla, of a Tyrannosaurus rex recovered from the Hell Creek Formation. The bone is stained a deep, mottled brown from the iron-rich minerals in the rock. The teeth still rooted in the sockets are the size of bananas, thick and heavily serrated. During the late Cretaceous, about 68 million years ago, this was the primary biological threat to any megaherbivore on the floodplain. If we want to know whether a T-Rex could bite through the shock-absorbing armor of an Ankylosaurus, we cannot simply smash a fossilized tooth into a fossilized osteoderm. The physics must be reconstructed digitally. A researcher carefully waves a handheld 3D scanner over the Tyrannosaur skull. A grid of green laser light pulses across the bone, capturing every curve, every tooth socket, and every deep indentation where muscles once anchored. On the monitor, a high-resolution 3D mesh of the skull slowly builds itself in real time. Once the digital geometry is complete, the skull is loaded into biomechanical modeling software. Here, the researcher maps the missing soft tissue. By analyzing the massive attachment sites at the back of the skull and along the lower jaw, they can estimate the volume and cross-sectional area of the jaw musculature. These digital muscles are then assigned physical properties based on the biomechanics of modern archosaurs. Like crocodilians and birds, when the simulation runs, the digital muscles contract. The software calculates the force transmitted through the jaw joint and down to the tips of the teeth. The results are staggering. Digital models map adult Tyrannosaurus rex bite forces exceeding 30.000 newtons at the back teeth. SRC04, Bates and Falkingham. 2012. To put that number into perspective, a modern lion generates roughly 4.000 newtons of force. The T-Rex was operating on an entirely different mechanical scale. Its jaws were not designed merely to slice through flesh and let the prey bleed out. They were engineered to shatter bone. We do not just have to trust the computer model. The fossil record provides direct, physical evidence of this capability. Paleontologists frequently recover large coprolites, fossilized feces, from the Hell Creek ecosystem that are packed with jagged, crushed shards of dinosaur bone. The T-Rex routinely consumed the skeletons of its prey, subjecting them to immense hydraulic pressure before swallowing. So, what happens when 30.000 newtons of force meets an osteoderm designed to absorb impact? We bring the digital models together on the wireframe. When the T-Rex jaw closes over the thickest part of the ankylosaur's dorsal armor, the physics equation becomes incredibly tense. Yes, the Tyrannosaur had the raw mechanical power to crack the bony plate. But raw power is not the only variable in a biological system. A researcher picks up a pair of digital calipers. They measure the width of a single T-Rex tooth. They then move to a cast of the ankylosaur's cervical plates, the half-rings of armor that protected the neck. They measure the narrow gaps between these heavy, raised bumps of bone. The spacing is incredibly tight. If a T-Rex attempted to bite down directly on the center of the armored back, it would not hit a flat surface. Its teeth would strike a jagged, Irregular landscape of hard keratin and dense bone. A misaligned bite. Driven by 30.000 newtons of force. Carries an extreme physical risk. If a tooth strikes the sloping edge of a heavy osteoderm at the wrong angle, the sheer force of the predator's own jaw muscles could snap the tooth at the root. Worse, it could fracture the jawbone itself. The armor did not need to be totally impenetrable to be effective. It only needed to make a direct attack mechanically dangerous for the predator. By presenting a surface with no clear, flat purchase points, the armor drastically narrowed the margin of error for a successful bite. If biting the top was too dangerous, a predator operating on a strict caloric budget had to find an alternative angle. The T-Rex jaw was a devastating weapon, but its effectiveness against this specific prey required finding a gap in the fortress. We must look at the constraints of the armor to find where that fortress ended. The digital wireframe model of Ankylosaurus magniventris rotates slowly on the screen. From above, the animal looks nearly unassailable. It appears as a wide, flattened oval shielded by hundreds of interlocking bony plates. But as the camera pans downward, tilting to view the animal from underneath, the limits of its biological engineering become starkly visible. We do not have the complete underside of an Ankylosaurus preserved in the Hell Creek Formation. Because ventral material is missing, we must look to more complete relatives like Euoplocephalus to confirm the belly lacked heavy armor plating. SRC01, Arbour and Curry. 2015. This is a fundamental constraint of armor. If you plate the entire body in rigid bone, the animal cannot bend its knees to walk, and it cannot expand its ribcage to breathe. Evolution favors protection only where it is strictly necessary. For a low-slung quadruped, the belly is almost never exposed to a threat. The heavy dorsal plates, the cervical half-rings around the neck, and the spiked osteoderms along the flanks were all designed to handle downward and lateral strikes. The underside was soft. It was composed of tough hide, muscle, and a massive digestive tract necessary to process huge quantities of fibrous late Cretaceous vegetation. This unarmored underbelly represents the only truly viable, catastrophic attack vector for a predator. But recognizing a weak point is very different from accessing it. On the digital grid, a new overlay appears, the center of gravity. During the late Cretaceous, about 68 million years ago, an adult Ankylosaurus magniventris is estimated to have weighed around 8 tons. Crucially, that mass was not suspended high off the ground like the body of a modern elephant. It was concentrated incredibly low. It was supported by 4 short, immensely powerful limbs placed wide apart. This low, wide stance created a profound biomechanical advantage in stability. If a T-Rex recognized that the belly was the only safe place to bite, its only tactical option would be to destabilize the ankylosaur. It would have to flip an 8-ton animal on its side or back, using the wireframe. We can calculate the physics of this maneuver. To topple an object with such a low center of gravity and a wide base of support requires an immense application of lateral force. A T-Rex could not easily use its jaws to lift or roll the animal. The smooth, sloping armor on the flanks offered no handholds or bite points to establish leverage. It would have to use its own body weight, ramming or pushing against the armored side of the herbivore. But a T-Rex is a bipedal predator. While massive, its own center of gravity is balanced horizontally over a single pivot point, its hips, pushing against a solid, wide-based quadruped on muddy or uneven ground risks destabilizing the predator itself. If the T-Rex loses its footing and falls, it exposes its own ribs and legs to fracture. This physical reality narrows the hunt from a dynamic pursuit into an incredibly risky wrestling match. We see this exact defensive logic in modern megaherbivores. If you observe the interaction between a lion pride and an adult African rhinoceros, the defense is not built on invulnerability. The rhino's skin can be pierced by a lion's claws, but the rhino's sheer mass, its low-slung power, and the danger posed by its horn dictate the outcome. Defense in these massive animals is about deterrence, not passive shielding. But a rhinoceros has a horn. A triceratops has 3 horns and a frill. If the Ankylosaurus was just a passive, heavy dome of bone, a determined predator could simply wait for it to tire. It could harass the herbivore until it stumbled or made a mistake. Deterrence requires an active threat response. It requires a weapon that makes prolonged harassment too costly to attempt. To find that weapon, we must trace the evolutionary history of the animal, and look at a piece of anatomy that completely reframed our understanding of how this dinosaur fought. On the screen, a phylogenetic tree maps the evolutionary branches of armored dinosaurs. We look back to the early ancestors of the ankylosaurids. Animals like the nodosaurid roamed during the early to mid-Cretaceous. They carried heavy armor, wide bodies, and sharp spikes along their flanks. But their tails tapered off to a simple, flexible point. They possessed no heavy club. As we move forward in time toward the late Cretaceous, about 68 million years ago, a distinct evolutionary shift occurs. The theropod predators in these ecosystems were growing larger. They were developing massive, bone-crushing skulls. In response, a specific lineage of armored dinosaurs, the ankylosaurids, began developing an entirely new biological structure at the end of their tails. The tail club is a late evolutionary adaptation, correlating with the rise of increasingly large apex predators. SRC01, Arber and Curry. 2015. Evolution does not expend massive amounts of energy growing heavy, dense bone at the extreme end of an appendage unless that weight serves a vital function. But a massive lump of bone is completely useless without a delivery mechanism. If a tail is too flexible, the weight of the club simply drags on the ground. It becomes impossible to lift or control with precision. On the lab table, a series of fossilized vertebrae are laid out in sequence. These are the caudal, or tail, vertebrae of an ankylosaurid. As we examine the bones from the base of the tail toward the tip, their shape changes dramatically. Near the hips, the vertebrae are robust. They have wide spacing that allowed for a significant range of side-to-side motion. This base provided the swing, but as we move closer to the club, the vertebrae become highly modified. They elongate and flatten out. The joints between them tightly interlock to form a rigid column. This section is known as the handle. Visually, these interlocking bones suggest a stiffened structure. But surface observation is not enough to prove how the tail operated under extreme stress. To understand the internal mechanics of the handle, the bones are taken to a medical imaging facility. The heavy vertebrae are slowly fed into the bore of a high-resolution CT scanner. The machine captures thousands of X-ray slices, building a three-dimensional map of the fossil's internal density. Back on the computer monitor, the researcher scrolls through the black and white images, running parallel to the vertebrae. Embedded tightly along the bone are long, bright white lines of extreme density. CT scans of the caudal vertebrae show ossified tendons that transformed the flexible tail into a rigid handle. SRC02, Snively et al. 2009, in Life. Tendons are tough bands of connective tissue that attach muscle to bone. But in the tail of the ankylosaurid, these tendons underwent ossification. They literally turned to bone. They acted like biological steel cables, binding the interlocking vertebrae together into an incredibly stiff, unbending rod just before the heavy club. This changes everything. A flexible tail would have allowed the heavy club to snap back like a whip. But a whip relies on speed, and a heavy mass of bone cannot be moved fast enough to generate a whip crack. By stiffening the handle with ossified tendons, evolution turned the tail into a rigid bat. The heavy muscles at the base of the tail near the hips provided the swing. The rigid handle then transmitted that force directly into the club, without losing kinetic energy to flexibility along the way. But a rigid bat presents a massive biomechanical problem. When a baseball player swings a bat and hits a pitch, the vibration travels down the wood and stings their hands. If an ankylosaur swings a massive club of solid bone into the leg of a charging predator, the kinetic energy of the impact does not just stop at the target. The shock wave travels straight back down the rigid handle. If the internal structure of those interlocking vertebrae could not handle the stress, the ankylosaur would shatter its own spine upon impact. A weapon that destroys the user is an evolutionary dead end. To determine if the tail was actually a viable weapon, we have to apply the laws of physics to the biological model. We must measure the forces involved when the ultimate armor strikes back. The digital wireframe model of the ankylosaurid tail is isolated on the screen. The heavy club, the rigid handle reinforced by ossified tendons, and the muscular base render in crisp 3D geometry. We have established the physical mass of the weapon. During the late Cretaceous, about 68 million years ago, the bony knob alone on a large adult weighed nearly 40 kilograms. We have mapped the swing radius allowed by the flexible vertebrae near the hips. Now, we must test its structural limits. Researchers do not rely on guesswork to find these limits. They employ a method borrowed directly from aerospace engineering, finite element analysis. Software usually used to test airplane wings against turbulence now analyzes fossilized bone. The program breaks the 3D model into a mesh of thousands of tiny, interconnected geometric shapes. The researcher assigns specific material properties to these elements. They input the density of fossilized bone and the estimated elasticity of the missing cartilage. With these variables set, the software can simulate exactly how mechanical stress will flow through the structure under extreme conditions. The researcher initiates the simulation. On the screen, the digital tail swings outward. It strikes a rigid vertical barrier. Instantly, the gray bone of the model flashes into a brilliant spectrum of color. This is the stress heat map. Blue indicates low stress. Yellow means moderate stress. Red marks points of critical failure, where the bone would crack or shatter. When the 40-kilogram club makes impact at high speed, the stress does not travel down the handle. The interlocking vertebrae and the ossified tendons perform exactly as their biological design suggests. The heat map shows the stress concentrating heavily on the outer surface of the club, right at the point of impact. The rest of the handle remains a safe, cool blue. Finite element analysis demonstrates the tail could withstand impacts generating up to 15.000 newtons without fracturing. SRC02, Snively et al. 2009. This number is the definitive turning point in our understanding of this animal. 15,000 newtons of force is not a warning tap. It is a catastrophic, bone-shattering kinetic event. It is roughly equivalent to being struck by a small car moving at low speed, with all that energy concentrated onto a surface area no larger than a bowling ball. When this force meets the long, load-bearing bones of a bipedal theropod, the result is devastating. It is easily enough to fracture the femur or the fibula of an adult Tyrannosaurus rex. The passive, slow-moving tank of popular imagination is completely dismantled by this data. The thick osteoderms and the shock-absorbing woven bone were not there simply to help the animal endure a beating. The armor was there to buy time. It protected the vulnerable spine and neck just long enough for the ankylosaur to plant its feet, rotate its mass, and deliver a devastating counterstrike. But recognizing the sheer destructive power of the tail club introduces a final, critical question. If the T-Rex had a bite force of 30.000 newtons, and the Ankylosaurus possessed a swing capable of 15.000 newtons, what actually happened when these two biological extremes shared the same floodplain? To answer that, we have to pull back from the microscopic tissue and the digital physics. We must look at the scattered bones of the Hell Creek Formation one last time. We are no longer looking for isolated specimens. We are looking for the scars of a biomechanical arms race. To map the harsh economic reality of survival, a single fossilized bone rests under the harsh lights of a photography stand. It is a fibula, the thinner of the two long bones in the lower leg of a large tyrannosaurid, about halfway down its length. The smooth curve of the bone violently bulges outward into a massive, swollen lump of deformed tissue. This is a callus. It is the physical hallmark of a healed fracture. During its life in the late Cretaceous, about 68 million years ago, this massive predator suffered a catastrophic blunt force trauma to its leg. The bone cracked entirely. Yet, the animal survived long enough for new bone to bridge the gap and fuse the break back together. It is incredibly tempting to point to this specific pathology and declare it the definitive aftermath of an Ankylosaurus tail strike. The height of the injury aligns perfectly with the estimated swing radius of the heavy club. The sheer blunt force trauma required to snap a theropod leg bone flawlessly matches the 15,000 newtons of force calculated in our digital models, but paleontology demands strict adherence to what the evidence can actually prove. We cannot know if this specific Tyrannosaur was struck by an Ankylosaur. It may have been kicked by a struggling Edmontosaurus. It may have simply fallen violently against a tree during a hunt. Connecting a specific healed fracture definitively to a specific prey animal is impossible. What this bone does prove, undeniably, is the extreme peril of being an apex predator. This healed fracture represents a prolonged period of starvation, pain, and vulnerability. A bipedal predator with a broken leg cannot pursue fast prey. It cannot easily defend its territory from rival tyrannosaurs. Every hunt carried the risk of severe injury. In an ecosystem without a safety net, an injury operates as a delayed death sentence. This reality fundamentally shifts how we must view the interaction between Tyrannosaurus rex and Ankylosaurus magniventris. We have proven that the T-Rex had a jaw capable of 30,000 newtons. It was strong enough to pierce armor, provided it could find a clean angle without snapping its own teeth. We have proven the Ankylosaurus possessed a 15,000 newton weapon, heavily guarded by shock-absorbing osteoderms. But biological success is not about winning fights. It is about caloric math. A map of the Hell Creek specimen density reappears on the screen. The vast majority of the icons represent the remains of Triceratops and Edmontosaurus. These herbivores were abundant. While Triceratops possessed dangerous horns, and Edmontosaurus could deliver a powerful kick, neither possessed the near 360-degree, bone-shattering defense of a healthy, adult Ankylosaurus. For an apex predator calculating the risk of starvation against the risk of a shattered leg, the math is brutally simple. A healthy, fully grown Ankylosaurus represented an incredibly high-risk, biologically expensive meal, sitting in an ecosystem filled with easier calories. This does not mean the Ankylosaur was never eaten. We find trace evidence of consumption scattered throughout the fossil record. A close-up photograph shows an isolated piece of Ankylosaur bone. It is deeply scored by the parallel, V-shaped gouges of theropod teeth. But when we map exactly where these bite marks occur across various specimens, a distinct pattern emerges. Trace fossils show theropods routinely consumed juveniles or scavenged carcasses, completely mitigating the extreme risks of hunting massive adults. SRC05, Hone and Ruhoot. 2010, a juvenile ankylosaur lacked the dense, woven bone armor of an adult. Its tail club was smaller, lighter, and incapable of generating the catastrophic force needed to deter a massive predator. Disease, old age, or a simple misstep in deep mud could also render an adult vulnerable to an opportunistic T-Rex. Furthermore, distinguishing between a predator executing a successful hunt and a scavenger simply processing an animal that died of natural causes remains exceedingly difficult when we only have tooth marks left behind. The epic, thundering deathmatch of popular myth was likely a rare failure of judgment. It was a desperate act by a starving predator, or a tragic mistake by a sick herbivore. What the rocks of Hell Creek actually preserve is an evolutionary stalemate. It is the story of a heavy, slow-moving animal that sacrificed agility, encased itself in shock-absorbing woven bone, and biologically cabled a massive hammer to its spine. It did not evolve these traits to become an invincible gladiator. It did it to force the ultimate predator to recalculate the cost of a meal, and simply walk away.